In a previous video, I solved Cauchy's linear equation. However, Cauchy introduced and solved not just one, but four functional equations which have become the cornerstone of the theory of functional equations. In this video, I will solve the second Cauchy functional equation, also known as the exponential equation, with the requirement that the solutions are continuous. For the solution of Cauchy's second equation, I will present two methods. The first method uses a transformation to reduce the equation to Cauchy's linear equation. Since the first equation has been solved, its solution is then used to obtain the solution of the second equation. The second way uses the ZQR method. As has been commented, the name of the method was introduced by mathematician Costas Efthimiou in his book Introduction to Functional Equations, and it is based on the fact that the method solves the equations in three stages. In the first stage, the equation is solved for the integer numbers. In the second stage, the equation is solved for the rational numbers. And finally, in the third stage, the equation is solved for all real numbers. It should be mentioned that Efthimiou called the method NQR and not ZQR, since often the domain of the function does not include negative numbers. However, for the first two Cauchy equations, the domain includes the entire set of real numbers, and hence I opted for ZQR. The passage from the second to the third stage makes use of two important facts. The first fact is that any real number can be represented as the limit of a sequence of rational numbers. The second fact is that the continuity of a function allows the exchange of the limit and the operation of the function. We are ready now to work out the solution of Cauchy's equation using the first method. Towards this goal, we can easily see that the function which is identically 0 is a solution. But this is a trivial solution. A non-trivial solution cannot be identically 0. That is, there's at least a point where the function is non-zero. In fact, a non-trivial solution cannot vanish at any point, since if it vanishes at 1, it will vanish at all points. To see this, if f were 0 at x0, then the sum x plus x0 produces all real numbers y. Then, from Cauchy's equation, f of y vanishes. Now let's set x over 2 in place of both arguments x and y in Cauchy's equation. Then, it is immediate that f of x is non-negative. Therefore, the function f is strictly positive for all real numbers. The last result allows to introduce the function g, which is the logarithm of the function f. It is now straightforward to see that, by taking the logarithm of Cauchy's second equation, we recover Cauchy's first equation in terms of the function g. We have thus transformed the second equation to the first equation. And if f is continuous, then g is continuous too. Therefore, the general solution for g is c times x, with c being an arbitrary real number. Applying the inverse transformation, we find that f is an exponential function with base b, where b is any arbitrary positive real number. And with the last statement, we have concluded the first method. We are moving to the second method. This method works even if we fail to see the previous substitution or the solution of Cauchy's linear equation cannot be considered known. First, we rewrite the given equation to include any number of arguments. The modified equation will be used to find the result for integers and rational numbers. Hence, in the defining equation 1, we set x1 for x and x2 plus x3 for y. This results in a similar functional equation, but for 3 arguments. We can repeat this process to get an equation for 4 arguments, and an equation for 5 arguments, and so on for any number of arguments. Now, in equation 2, we set all arguments equal to 1 to find that the value of the function at n is equal to its value at 1 raised to the power of n. Let's set the value of f at 1 equal to b, where b is an arbitrary positive real number, which cannot be determined. Returning to equation 2, we set all arguments equal to 0 to find that the value of the function at 0 can only be 0 or 1. Since the function is strictly positive, the value of the function at 0 can only be 1. Therefore, we have found that the value of the function at any natural number n is b to the n. Then, setting minus x for y in the original equation, we see that f at minus x equals the reciprocal of f of x. This implies that the result found for the natural numbers is true for all integers. To see this, in the last equation, substitute x by a positive integer n. Returning once more to equation 2, we set all arguments equal to the fraction m over n, where n cannot be 0. The resulting equation shows that the value of f at the fraction m over n is equal to the number b raised to the fraction m over n. Therefore, the function f of x has the exponential form b to the x for any x that is a rational number. If x is a real number, let's represent it as the limit of a sequence Qn of rational numbers. Then, the value of the function for any member of the sequence is b raised to that member. In the limit of n to infinity, the continuity of the function allows to exchange the limit with the function and find that f of x is b to the x. Conversely, any function of the form b to the x satisfies Cauchy's second functional equation. Therefore, we have proven that if the function f is required to be continuous, Cauchy's second functional equation is solved by the exponential functions of the form b to the x, and only them. In a follow-up video, I will show you how to solve the equation without requiring continuity of the solutions. I hope you liked this video. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.